Many developers approach GitHub Copilot as a deterministic search engine, but the system functions as a probabilistic engine, generating code based on statistical likelihood rather than a lookup of static, verified answers. This behavior stems from the nature of generative large language models. Unlike discriminative models that classify existing data, generative models produce novel outputs by recognizing and applying patterns derived from their training corpus. The underlying architecture relies on token prediction. For every character typed, the model calculates the likelihood of the next sequence of characters based on the context it is shown. Because the output is probabilistic, the model can generate different results for the exact same prompt across multiple sessions. It is important to remember that the model does not understand programming logic. It is generalizing statistical patterns from billions of lines of public code to predict a plausible continuation. Implementing this technology in a professional environment requires a technical grasp of the inference pipeline, the strict boundaries of enterprise data retention, and the specific security biases inherent in model training. When statistical guesses are accepted as absolute truth, the developer risks bypassing the review phase. This reliance on probability over verification creates the specific conditions for data leaks and software vulnerabilities. To master the output, we must separate two distinct datasets: the static training data used to build the model, and the dynamic local context provided by your editor. The primary driver for any suggestion is hyperlocal, the file you are currently editing and the exact coordinates of your cursor. The editor supplements this with broader local information, gathering data from your other open tabs, active imports, and surrounding function signatures. This collective context is bundled into a single package, the inference prompt, and sent securely to GitHub servers. Once the prompt reaches the server, the model generates multiple potential completions and ranks them based on their statistical probability. The highest ranked completion is sent back to your editor, appearing as translucent ghost text. The system is constrained by what it can see. Copilot does not access closed files, and it has no visibility into unopened private repositories in your workspace. The user governs the final stage. Pressing Tab commits the suggestion to the file, while pressing Escape or continuing to type rejects it. Because Copilot relies entirely on the data it is shown, opening relevant reference files and writing descriptive comments is the primary way developers can actively control the quality and accuracy of the output. Organizational adoption often stalls on a single question: will proprietary code prompts be ingested to train the public model? Every completion request involves a telemetry payload. This includes the prompt itself, file paths for context, and metadata like your IDE version and language. Handling of this payload is determined by your licensing tier. For the individual plan, prompts and code snippets may be retained by default to improve GitHub's models. Individual users have the option to disable this. Toggling the privacy setting prevents prompt retention for model improvement. The business tier operates on a zero retention architecture. For business users, GitHub discards the prompt immediately after the completion is generated. Your code is never stored and never used to train the base model. The enterprise plan mirrors this zero retention rule, but adds centralized audit logs, allowing administrators to track usage metadata without capturing actual code. Unlike the individual plan, where settings are managed by the user, the business and enterprise tiers allow organization owners to enforce these policies across every seat in the company. These tier-based boundaries ensure that enterprise intellectual property remains structurally isolated from the public model's training process. Even with strict privacy, we must address the quality of the suggestions. Because the model trains on public code, it inevitably inherits the public's mistakes. This manifests as popularity bias. Copilot often suggests the most common pattern found in its training data, like outdated hashing algorithms, rather than the most secure or modern best practice. Recency bias presents a similar challenge. The model often predicts deprecated APIs simply because they were widespread in older, popular repositories. These biases are amplified by human confirmation bias. Developers frequently accept code that compiles and runs without checking for the subtle logic flaws the model inherited. This is visible in the suggestion of hard-coded credentials. Because the model has seen countless examples of plain text passwords in public scripts, it will often offer them as a completion for your own variables. The same pattern applies to SQL injection vulnerabilities. The model frequently generates raw string concatenations because they are prevalent in legacy training data. These risks define the never accept zones. Custom cryptography implementations, core authentication logic, and user input validation must never be offloaded without senior-level human review. We also see language bias. The engine's accuracy declines significantly when working with niche programming languages that have smaller footprints in the training data. Copilot accelerates your current trajectory. If you don't actively filter the suggestions, you risk accelerating the adoption of the internet's worst security habits. Beyond security, organizations face a legal hurdle: the risk of the model generating code that matches licensed open-source software verbatim. Copyleft licenses, like the GPL, can require derivative works to be made open source. For a proprietary codebase, accidentally committing this code can lead to significant legal complications. GitHub addresses this with a specific technical safeguard: the public code matching filter. The filter compares every generated suggestion against millions of public repositories. It triggers a block if it detects a verbatim match exceeding 150 characters. When a match is found, the filter can either provide a reference to the original source or block the suggestion from the editor entirely. Critical organization and enterprise administrators can force this setting to blocked, ensuring that potentially licensed code never enters the developer's IDE. Utilizing this duplication filter allows companies to use generative AI while protecting their intellectual property from license contamination. Transitioning to an AI-assisted workflow requires a pivot from writing syntax to validating logic. Copilot should never be the final step in the pipeline. It must be paired with static analysis tools and security scanners to catch the vulnerabilities that the probabilistic model inevitably suggests. GitHub's responsible AI principles emphasize this necessity. You must review every suggestion, understand the code before committing, and rigorously test for edge cases. Critical architectural decisions and security-sensitive logic remain the responsibility of the developer. These cannot be offloaded to an inference engine. While privacy policies and duplication filters provide the framework for safe use, the ultimate security boundary is the developer's expertise in validating the model's probabilistic guesses.